Okay, we're going to start out with 140. We're going to talk about magnetic principles.
Okay.
Yesterday, or last quarter I should say, which kind of sort of was yesterday, we talked about inductors. Do you remember the discussion that we had about inductors?
Yes, sir.
And we said that an inductor was a coil of wire wrapped around some central core. Right?
Yes, sir.
And what we said was, when we pump current into there, it develops a magnetic field and stores current by converting it to magnetism. And then when the current goes away, the balloon discharges back into the wires and converts magnetic energy into electrical energy. So what we're actually doing is converting between electrical and magnetic energy.
Okay.
Good?
Yes, sir. Here we go.
Okay, what we really didn't talk about is what's going on in that process, and now we need to look at this in a little bit more detail.
Okay.
Okay? If I look at the direction the current is flowing, I can see that it's flowing around this way. Right?
Yes, sir.
So if I were to take my fingers and wrap them around in the same direction that the current's flowing, my thumb would point to North Pole. So what I've actually created is an electromagnet. If we want to stretch our imagination a little bit, what I've actually created is an electromagnet. This is the same type of device that's used to pick up cars at the junkyard. You can turn it on and off. It's not the same as a permanent magnet. A permanent magnet is a piece of rock that you find in the ground that naturally has a north and south pole. It's called lodestone.
Huh.
It's magnetic, just the fact that it exists is magnetic. When you rub it against something else that's capable of storing magnetic energy, like iron, then it will impart some of that magnetic energy, just like voltage will impart itself onto anything that will conduct.
Okay.
Okay? We're able to make that happen by taking a non-magnetic material that is susceptible to magnetism, like iron, and putting a coil around it and running current through that coil will make us a magnet.
Okay.
Okay? That's part one. Here's part two. I take the same coil and instead I take a magnet and rotate it, moving it past the coil. It will generate current. So if I go down to the hydroelectric dam and I connect this up to a big turbine and put water through the turbine, turns that magnet, rotates it next to that coil, generates current. That's how we make power hydroelectric dam. That's
Nice.
one of the ways we can do it. We can do it with wind. We can do it with any type of natural motion we can convert into this process.
Okay.
So we're talking about power generation here. Here, we're simply talking about storing magnetic energy and unstoring it when the initial source goes away. It's like blowing up a balloon, and then when you take your mouth off the balloon discharges what you've blown into it.
Okay.
Same basic idea there.
Okay.
Okay, and the third part of the equation we'll put over here, and that is where we take a north-south magnet and we put an AC signal coming in, which gives us pole reversal.
Okay.
And that then, because of the attraction and repelling of like charges, will cause this to spin to try to get away from the North Pole. And spin because the South Pole then will be attracted to this pole, which is north. Then when it gets there, we change, the AC then changes the polarity and makes it keep spinning. It's kind of like putting a carrot on a stick in front of a horse. You just keep leading that North Pole around in a circle, and you know, we may have the other coil on the other side. We could have any number of coils. When we start talking about three-phase, then of course we're going to multiply the number of coils by 3 to go in that route. But you can see in this situation, if we continually reverse the poles, another way to look at it is to look at it this way. Let's put AC here. That gives us south and north. And let's put AC here, and that gives us north and south. What happens when the AC changes polarity? This becomes south, this becomes north. North repels north. This wants to get away from this North Pole.
Nice.
North becomes south and south becomes north. Here, south wants to get away from its same pole because like poles repel.
Right.
And it's going to turn and flip over this way.
Nice.
But before it gets there, we'll switch it again. And every time it gets close, we're going to switch it. The momentum of the motor itself is going to carry it past that point, and it's going to keep pulling it around in a circle. And we're making that happen using magnetism, changing electricity into magnetism, creating and inverting magnetic fields. And we're going to learn how to do that for DC as well this quarter so that we can run motors off of DC as well as AC.
Sweet. Nice.
Okay, good?
Good to go.
All right. You've been through all the discussions of reactances and impedances, and we've dealt with all of that math.
Mm-hmm.
That math, as of this quarter, goes away,
Oh.
which is good news. As we move into third quarter, we start to look at larger and larger systems.
Okay.
We stop looking at things under a microscope and we start looking at things like, how can we use this?
Okay.
What can we do with this?
Okay.
Because ultimately, it's not what you know, it's what you can do. And this is kind of the beginning of where we start to be able to do stuff.
Okay.
We're not building little circuits on circuit boards, although you will in the 126 class. But in the 140 class, we're going to be working with the ladder logic boards, and we're going to be simulating real-world processes.
Nice.
And a lot of that has to do with reactance. Anytime we close a relay coil or a contactor coil or energize a timer, there's reactance taking place in that process. When we're talking about delays, we're talking about RC time constants, capacitors. things like that. When we talk about motors, which is part of the title of this course, we're talking about inductance and magnetism. So we won't talk about resonance very much, although it will occasionally rear its ugly head. But for the most part, we're talking about motors and how we control motion. Not just the motion itself. The motor theory represents a fairly small portion of this course. But we're going to be getting into sensors, transducers, switching circuitry, ladder logic, to work on how do we control these motors. Not just the motors, but how do we control them. So both of those things will be mixed together in this course. This is the fundamental logic of most of what we're going to cover.
Okay.
It all involves magnetism. Okay, questions?
Yes, sir.
All right, that's good. We're going to move into our next topic then. Tomorrow in 140, we do have lecture tomorrow in 140, I believe. No, we don't have lecture tomorrow. We'll have lecture on Monday in 140.
Okay.
On Monday, we will start to look at safety.
Nice.
Because before we actually do any of these things, we're going to be working with 110 volts AC this quarter. No longer the safety zone, relative safety zone of working with DC 5 and 10, 12 volts.
Right.
This is stuff that can set you back a little bit. So we want to make sure that we are following industry protocol. If you look over there, you'll notice that the fuse panel that's on those boards has a lock on it. Can you see the red lock that's on there?
Yes, sir.
We're going to spend most of the day on Monday talking about that as a process. It's called lockout tagout. It's a way to make sure that somebody doesn't inadvertently come over and turn that on while you got your hands in stuff. So, you know, all that stuff is a process, there's a procedure, there's an industry standard that we have to discuss relating to how we keep safe when we're working on higher voltage, higher potential sources.
Okay.
Okay? So let's move into 126. I'm going to turn this off and turn it back on again.
Sure.